All right, let's take a look at a graph problem. Flight routes, so what's going on here? We should find k shortest flights from Pijala to Metsala. So that's interesting. Right? We've been doing like one shortest path. How do we do k shortest paths? If there's a tie in price, we can count all of them. Right, so in the example, we have a price 4, and then the next cheapest, I guess, is price 7. And so we should output 447. So it's a directed graph. The edges have weights or prices on them. The prices are but they're positive. So we don't need to worry about any negative paths, which is nice. K is up to 10. The graph is 100,000 by 200,000. And we want to go from 1 to n. So this looks like a Dijkstra kind of setup, right? If k equals 1, this would just be like normal Dijkstra. But k can equal 10, so what do we do? So it turns out that we're going to do Dijkstra, except we're going to keep track of the first k times that we visit each vertex instead of just the first time that we visit each vertex. And so the claim is going to be that, you know, the kth time we visit the vertex, that's like the kth cheapest path to that vertex. And yeah, I guess that's pretty much it. So like, why should that be true? It's because, right, so Dijkstra is basically like exploring all paths in the graph. And so the usual argument about Dijkstra of like the cheapest path, like is the cheapest path to that vertex, right? So like the cheapest path in our priority queue is the cheapest path to that vertex. Like that's still correct. And just the point is that like the second time we see a vertex, that's the second cheapest way to get to that vertex. Yeah, so like, I don't know, it's the same idea for Dijkstra. It just goes through with, you know, with higher k. And we need to visit all, you know, so why do we need to visit all of the vertices at most k times? What if like the kth shortest path from 1 to n uses the k plus 1 shortest path to some other vertex? Well, it can't, right? It should just use the k shortest paths instead. It'll never get, you might need to use like the k shortest paths to some intermediate vertex. If like if you've already used the best path to that vertex, right, you need to switch it up for the next path. But you'll never need to use more than k paths through some intermediate vertex because we're only looking for k total paths, right? You could just use them once each. So yeah, that's it. Let's code it up. N and k. And we just read n lines. Minus. Right, so for every vertex, we're going to keep track of the edges coming out of that vertex. The one way. Okay, so we do that. Priority queue. So as usual with Dijkstra, we want to reverse the order of the priority queue. So we pass in greater. This is going to be a pair, right? This is going to be distance and the vertex. This is the vertex and the cost. Q dot push pair, right? So initially we're at the start. And we want to track the k shortest distances. Yeah, we'll just do it like this. The k shortest distances to each vertex. So we have normally this would just be a vector, but we want k distances, so it's a vector of vectors. So if you've already been to this vertex k times, continue. Otherwise, we should visit it again. So add the current distance, right, the current path to the list of distances, and consider every edge out of this vertex as a new path. Yeah, I don't need to do make pair. This is d plus c y. Okay, and that's it. And now we just need to print out the k things that we found for d of n minus 1. Yeah, okay, and it's guaranteed that that actually happens. Instead of make pair, you can just do braces, maybe a little nicer, so it is shorter. Okay, so we want IO stream, we want vector, we want utility, has pair stuff, namespace stood, LL, PLL, pair, and that should be it. And Q, so priority Q. Fair enough. Four, 447 looks good. Flight routes. Cool, so that works. So yeah, this is like really almost identical to normal Dijkstra. The only differences are we have a vector for the best distance instead of a vector of vectors instead of a one-dimensional vector. And instead of just checking if we've already seen this thing, we check if we've seen it k times. We push back a best distance instead of equal assigning it. But other than that, it's like identical. And of course, you print out the k distances at the end. So yeah, it's kind of neat that Dijkstra extends so easily to this case. Cool thing to know.